Um, I am very happy to introduce the today's the next speaker in our seminar, the Math UP seminar, Shend Zhjeqi, who is a PhD student at the University of Michigan and who has already forged a brilliant career, and we're very, very happy to have him with us, obviously online. So it's very early in the morning over there in Michigan, and we thank you for your time, and we look forward to your presentation, Shend. Thank you.
Thanks for having me. Yeah, so today we're going to be talking about bend and break. The plan is for the first half or so to basically do an introduction into AG, and then afterwards I'm going to start talking about bend and break. So let's start. Okay. I'll start off basically with, so I guess first thing is, what is AG? Algebraic geometry. Well, the basic idea of algebraic geometry is to study solutions of systems of polynomials. So if I have a bunch of polynomials and I set them equal to 0, I want to understand the solution set for those. And the idea is that those polynomials, I can either look at them algebraically as equations or think of the space that they cut out. So in a way, I can see algebraic geometry as a way to move information between algebra and geometry. Okay, so move information between algebra and geometry. And the fundamental objects of interest are called algebraic varieties. And so I'll put in brackets classical algebraic varieties. To mean, and the definition for this is going to be basically, if I have a bunch of variables x1 to xm, I'm going to look at the solution set p1 pn equals 0. And that's going to be some space inside. So for example, if I have one variable, say x, then I can look at the polynomial x minus 1, set that equal to 0, and that's just the number 1, right? Or what I can do, I can have two variables, x and y, and I can think about x squared plus y squared equals 1, and that's going to be all the points of the unit circle. So that's going to be my algebraic variety. Okay, my classical algebraic variety. And so, right, those are two examples, and both of them satisfy the condition. I have some polynomials. In both of those cases, I have one polynomial and a bunch of variables, and I'm setting those equal to 0. I can rewrite this to suggest that. Okay. Oh, by the way, if anyone has any questions, feel free to interrupt me. Like, the point of this is to make sure we get the most out of it. So, yeah. Some more examples that involve more than just one polynomial. You could take x equals 0, which is basically like killing a variable in some sense. And then we have y squared plus z squared equals 1, which is the same picture as this, but just sitting inside the three-dimensional space. Okay, so let's linear circle like that. So we can see like all those are like very familiar objects, and we would want to be able to say interesting things about them if we can. And so classical AG, I want to give some more interesting examples in the sense that they are not quadratic. So x squared times x plus 1. Okay, so in two variables, y and x, this thing is something on the plane, and it looks basically something like this. And there's a node here. Yeah. The strange thing when you look at this picture and compare it to those two, I guess this and those two, is that there's a self-intersection. So even though I haven't defined smoothness, if there was like a concept of smoothness that would respond to our intuition, this point shouldn't be smooth. There's like self-intersection, that's bad. And so one concept which I'm not defining right now, if people want me, I can do that. So yep, feel free to ask. Is basically, right, is the variety smooth? That's one question we could ask. And for those, for just the point and for the circle, the answer is yes. But if we do something like this equation, we see that's not the case. And if we do something like this, you also see that that's not the case. And the picture, when you have y squared equals x cubed, is something as follows. In this case, there's no self-intersection, but there's still some kind of non-smoothness. And to have a better idea, like how would one define the smoothness, at least even like intuitively, you can think about the dimension of the tangent space, meaning you look at all the tangents to the graph that approach this point. And in this case, you see basically that there's two directions, and those two directions somehow allow you to span the whole plane as vectors. So the dimension of the space of tangent lines to this graph is two-dimensional. And because that is bigger than the expected dimension at other points, so at other points, the dimension of the tangent lines is just one. And so you can see that as you're going to this point, the dimension of the tangent space, which I also didn't define, is just all the vectors in some sense that are tangent to that point. But you can see that here there's a problem of how to defining tangent. Like, what does it mean to be a tangent there? But if you think about the, as I said, the lines that are tangent to other points which are smooth and go to this, then you see you get two different directions, and you can use those to span the point. And this is basically, you can make this precise. I will in a few moments. So, right, we can see that we can we can understand, well, at least we can ask whether a variety is smooth, and it turns out it's not too hard to calculate to know if a variety is smooth or not. What's more problematic is, can say that the variety is not smooth. Can we do something to make sure that it becomes smooth? So what I mean by that is, I need to create, so I want to get rid the singular point. And for that, I would want to have something like, it's best to start from an example. So say I have the nodal curve. So this is called the nodal curve. Okay. And say, so let me rewrite the equation, and I want to have the graph again, like this. Say that we consider all the lines that go through this point, okay, like that. So let me make it in color. I'll just draw. And if we think about basically parametrizing all those lines, then what we're getting is a one-dimensional family, meaning that there's really one direction this way that you can move the lines, change the slope, right? Is basically parameterized by the slope of the line, which spans all the other points in this curve. So let's do something as follows. For each of those lines, intersect them with a chosen, so extend those lines and intersect them with a chosen line L, okay? And project the second point of intersection. For this line, it would be this point to this point P. So this point P prime is projected onto this point P. And as you move on the circle, so this point Q prime will be surjected onto, will go to Q, okay, and so on. Q double prime, or maybe S prime and S. Okay. It turns out that this mapping is basically an association between the points on the curve. So there's a point x comma y, so that y squared x cubed x plus 1, and we send this point x comma y to the slope, which I'll denote by t. So slope of the line by the way, I should have given some coordinates. The node is at 0, 0. Yeah. So xy will go to the slope of the line, which goes through 0, 0 and xy. Okay. And that is easily seen to be, that's y equals. So if I have a line that goes through the origin, I know that that line will look something like y equals ax, y equals tx, say. So t is y over x. So t is y over x. So our mapping is just x comma y goes to y over x. Okay. All right. So what's good about this? What's good about this is even though this is not a polynomial in x and y, it's a rational function. And it turns out that when you do algebraic geometry, rational functions are okay. So it's not just about polynomials. You can also do fractions of polynomials by polynomial. And now, having this mapping, we call this t. I'll go back to this equation, substitute this in, and I'll get something as follows: t squared equals x plus 1. right? So I can see that x is equal to y squared equals x squared times x plus 1, y equals dx. Yeah, t squared is x plus 1. So x is t squared minus 1. And then y equals t times x, which is t times t squared minus 1, right? What's nice about this form is that I've given a parameterization of all the points on the nodal curve, right? So I can plug in arbitrary t and get the point x comma y, which lives in this curve. And previously, like 2 minutes ago, it's not entirely clear, like for what values should you plug in for y and x to make this happen, to make this work. Okay, so another way to think about it is, in fact, this mapping is a mapping whichever way you go. So it's a way to map points on of the curve to the line, but it's also a way to map the points of the line to the curve. This one-to-one correspondence is actually like smooth. Is a smooth function both ways, and not just smooth. It's actually algebraic, because we can see that the coordinates x and y are algebraic functions of t, and also t is an algebraic function of x and y, meaning that it's given by ratios of polynomial. And what have we done so far? I've gotten this mapping from the line to the nodal curve, which actually gets rid of the singularity. So if we forget this point, so this point doesn't go anywhere. All the other points go somewhere. This point is just missing from the picture. And I've effectively changed my curve in a way that gets rid of the singularity. And this is called resolution of singularity. And resolution of singularities is really important for many things. And I'll just state, well, I guess what is known. If you have algebraic varieties, which are, well, I have to say several conditions, but basically, if you do algebraic varieties in the classical sense, the one we're talking about right now, then you can actually always resolve them, and you can do that in a nice way. I'll just mention that Hironaka solved resolution of singularities, at least like in the case I'm describing, meaning that if you have some kind of space system of polynomials with coefficients in, say, complex numbers, then that space, you can find a map to it. So if I give you a space x, you can find a map x prime to x. You can even say much more than that, but so that x prime is smooth. And you want to make and modify only the singular parts. Okay. So some other examples of spaces that I just want to write some notation for is an, which in the classical case, which is what I've been talking about, just k to the n, and pn k is you take k to the n plus 1, you remove the origin, and then you cross out by the action of k star by scaling. Okay, so that's also a space. This is called affine space. This is called projective space. Okay. Right. So why am I mentioning resolution of singularities? Well, bend and break is a technique that was developed in birational geometry. So I want to get to introducing birational geometry, which is a branch of algebraic geometry. And well, I'll say that what birational geometry wants to do is understand varieties up to lower dimensional subsets or subvarieties. And a subvariety is a variety itself, but it also sits inside our variety. Yeah. Are there any questions so far?
I think it's good so far.
Okay. So that's one goal, understanding varieties up to lower dimensional subsets. And another goal is resolution of singularities. Because I said Hironaka proved it in the classical case, but then there's other cases in which it's not known, and I'll get to introduce them right now. And that's where we get to the modern algebraic geometry, modern AG, where what's essential, like what's crucially different between modern algebraic geometry and classical is in the classical case, you only look at the solution sets in the geometric. So you can either look at it algebraically or geometrically, but usually people only look at the variety, at the points where the equation is satisfied. But it turns out that it's much better to remember the functions. So remember the functions on our variety. So what I mean by that is, let's take an. Previously, I defined it as kn. Now what I want to say is that, so this is the classical one. The modern A and K affine space is going to be a topological space plus functions on that space. And I want to say now precisely what the NK is. So the functions on that space is going to be polynomials in n variables. And the topological space, which is denoted as spec of kx1 xn, is going to be all prime ideals. All prime ideals of this ring, of the ring kx1 xn. Okay. We can do the same definition for any kind of ring. So if you give me a ring, I can remember that as functions on my space, and then I can take spec of that ring to be all prime ideals of the ring. And the modern definition of an affine scheme, modern affine scheme, is the collection of the pair of all the prime ideals spec R and the ring R. And what's the topology in spec R? Right now it's just a set. The topology is the minimal one that makes all the functions be continuous. And for that, you just need to say that where the functions vanish, that's a closed set. Okay. So that gives a topology on spec R. And the nice thing about thinking about the functions is I never need to say I can work with general rings. That's the first thing. So I could work over something that's not even characteristic 0. For example, say you have the ring R being Z mod P, right? This is a field. It is a point, but it's also remembering the field as well, right? Another case would be R equals Q. That's also a field. It has only one prime ideal to 0. But the functions on this and the functions on this are very different. So even though topologically they look just as one point, they're very different as a scheme. Okay. So what I want to mention is because I can say on things of on characteristic 0, so right, remark can do geometry, not just over C or R, for example, but also over finite fields. Finite fields, for example, so those are all FPNs, and not just that, but also over rings of any characteristic. All rings, and I'm going to specify full characteristics. Okay. Now, on the rings of positive characteristics, you have this map. So let R be a ring so that P is equal to 0. So P being a prime number, meaning that P is the characteristic of the ring. And I can do the following map. X goes to X to the P. In 0 characteristics over complex numbers, this map is bad, like it's not well behaved. Or rather, I should say, it's not a map of rings. So the map R goes to R, X goes to X to the P is not a map of rings in characteristic 0, so over complex numbers. But this is actually a ring map over characteristic P. And this is actually very useful. So this map for Venus, the existence of this map allows for so much connections and like work to be done. Right, even though it's like so simple. Okay. Now, what I want to say is I want to define what the projective variety is. X is a projective variety. So we saw what an affine variety is. It's spec R together with the ring R. So projective variety, I'm going to define it as, you can define it in a way that doesn't talk about any kind of embedding. But here, I don't want to do that right now. No, I mean, it's not, but if people are interested, I can say that. I'm going to define X, I'm going to say that X is projective variety if there exists homogeneous polynomials f1 fk in kx not xn, and then you look inside projective space. So previously I only defined this as a classical algebraic variety, but you can also define it as a variety in the modern sense. I'll just say briefly what it is. In the modern case, you need to have a ring that is graded, and this has grading. You can just put all the xi's to be in grading 1. And for project for graded ring is going to be all homogeneous prime ideals as a topological space. And then on each open set that is an affine open set, you can also describe what the functions are. I'll just say that much, right? And inside here, I'm going to look at the vanishing of f1 fk. So I look at all the points where all those functions vanish, and I want x to be equal to that. So I don't want to just remember, just the points where f1 fk vanishes, but I also want to remember x with the functions on x. And the way to do that is, I'll say to remember this ring, f1 fk. So you have to remember this ring. Yeah. Okay. Right. Now we have a notion of the projective variety. Now, why did I even introduce this? Well, the point is, there is something much better for projective varieties than for affine varieties, and that's that they're complete. And what that means is, if I were to, it's basically the analogous version of proper or of compact in topology. And that's like, even in topology, we know that compact spaces behave much better than non-compact spaces. So we would want to have something like that. All right. Last thing I want to say is, right, you can define the degree, degree of x in Pn. So say, yeah, you can define degree of x in Pn where x is one-dimensional. So say this is a curve, one-dimensional. So the degree of x in Pn is defined to be, so is the number of intersection points of x with a generic hyperplane. With a generic hyperplane. Oh, what's a hyperplane? A hyperplane is the vanishing of a linear polynomial in Pn. So something like, for example, 2x1 plus 3x3 plus plus x5. Yeah. Right. And what does generic mean? Well, you have to be a little bit careful, because if you take, it just means that the intersection with a curve, it's a finite set, and it doesn't contain any component. And in fact, you have to make it generic so that you don't intersect it like this. So say you have the circle, you don't want, unless if you count multiplicities, you don't want to intersect it like this. The lines you're going to choose to intersect it with, if they do this, then there really should be 2 points here, not just 1 point. That's actually one of the reasons why you would want the modern definition of algebraic geometry and not the classical one, is because in the classical sense, this intersection would be just 1 point. But in the modern sense, it turns out that the ring you're looking at, when you do this, the functions on the space are kx over x squared, which is, so it has a nilpotent. And if you look at the dimension of this is a k vector space, you see that it's 2, not 1. And that corresponds to the fact that here you really have 2 points in some sense. Right. Or a point, 1 point of multiplicity 2. That's better. Okay. I think now it's time to move into bend and break, which is going to be yeah, more slightly, yeah. Are there any questions?
I don't see anyone.
Okay. Section 2. So now we do bend and break. So I guess what's the point of bend and break? Well, Mori was trying to prove this conjecture, which Harshran's conjecture, which says that if conjecture, which he actually proved, the conjecture was made by Harshran, and it says if x, say x projective, and there's a notion of ampleness, which I'm not going to define, but NTX ample, then X has to be isomorphic to a projective space. So this is a really, really strong statement. But also this condition is really, really strong because it says something very restrictive about the geometry of X. For example, the way to think about it is unless if those words already make sense, I don't know if this will help, but a complex manifold. So a complex manifold, I assume, is that okay, or do I have to say? It's basically like, for our interest, it's just a smooth algebraic writing over C. That's a complex manifold. Has positive bisectional curvature. So if you have some kind of Riemannian metric, and also if you have tensors that are telling you that your curvature, your holomorphic curvature, have positive bisectional holomorphic curvature, is positive everywhere, then this implies that the tangent bundle is ample. So whatever this condition means, it is implied by having restrictions on the curvature of the space. Yeah, I didn't define curvature as well, but in dimension 2, I just want to say that you have a trichotomy where you look at objects. So you have projective line, which in fact is 2-dimensional as a real manifold, and it's a sphere. You have elliptic curves, and then you have higher genus. So yeah, higher genus. Genus bigger. So genus in this case is 1, here it's 0, and genus is just the number of folds in dimension 2. Genus greater than 1. In genus 0 case, the total curvature curvature is greater than 0, 0, and in this case is negative. And this trichotomy tells us that the only space that is projective and has Tx, well, if this was an equivalence, but the only space that has positive bisectional holomorphic curvature is projective on dimension 2 is P1. So the conjecture is true in dimension 2, not hard to show. Yeah, but in higher dimensions, it's entirely not clear what to do. But what Mori thought of doing was, okay, if we have curves in our space that are straight lines, so if they're really like P1s, things like this, those curves, if we restrict along those curves, those give us some restriction on the curvature. So the more P1s we have inside our space, the more restrictive the curvature of the space should be. And therefore, we might be able to say that if we have lots of curves, lots of P1s in our space, then in fact, the geometry of X is very rigid. And hopefully we can show that then X actually has to be Pn. But there are actually like many spaces that are even covered by P1s. But the point of the rest of the talk is going to be to mention what is, I'll be more detailed right now, to say that Fano varieties, I'll say what they are. Fano varieties are uniruled. The Fano varieties means it's smooth, where smoothness, I guess let's just assume that we know the definition for now. I can say it at the end. Smooth, projective. And if I look at the bundle, so I look at tangent bundle. On this bundle, I can take exterior powers. So I'm going to take the top exterior power. And this is going to be a line bundle. And I want this to be ample. So I want this to be ample. And under those conditions, those define a Fano variety. So smooth and projective, that's very general, but the restriction on exterior power of Px, that's the restrictive part. Then what is uniruled? I'll actually just say are covered by rational curves. And what's a rational curve? A rational curve is a map. It's a map from P1 to our X, to our Fano variety, to our variety X. Okay, X stands for our variety. All right. So how are we going to go about creating rational curves in our space? Because that's what bend and break allows you to do. It allows you to create rational curves, which ultimately allow you to control the geometry. So the idea is you look at the spaces so the morphisms from a curve to another space. And those are actually spaces themselves. And not just those, but also if you tell me these are all the maps C to X, where F. So what does it mean to be a map between C and X? It means that it pulls back algebraic functions to algebraic functions. Then F is an algebraic map, not an algebraic map. So on C2X, be those functions. This is a set. You can put a topology on it, and in fact, it's going to be an algebraic space. Right. Another thing that's going to be an algebraic space is going to be, you look at those morphisms, but you also ask, give me just the morphisms that send a fixed finite set to a fixed set of prescribed values. So this is going to be the list of all functions. So let me call this G. The list of all functions, where F is algebraic, F algebraic, so that F, when you restrict this function to B is a finite set, B inside the curve finite set, F of B is equal to G of B. This also turns to be a space, right? An algebraic space, right? So what we really want to say is the dimension of the space of maps from P1 to X is non-zero. We want maps from P1 to X, but how do you go about creating them? A very simple idea is take a curve that's not rational. You have plenty of curves inside your space, not necessarily rational. Take one and start deforming, to start bending it, and hopefully it will break. If it breaks, we have reduced the degree of the curve and also the genus of the curve. The genus may be the same if we have already, so say you have one curve inside your space and start deforming it. So we're deforming the curve and eventually it breaks. So at least one of the components. So if we keep doing this, if we can do it, if we keep doing it, we're going to get to a curve that is rational because we're going to be decreasing the genus for at least one of the components. So the question is, can we deform? So question one, can we deform the curve? And question two, will it eventually break? And the lemma one, is say you are given map from a curve to X so that the dimension of this space, so F restricted to C, the dimension of this at a given map. So what I mean by that is this is a point in this space. And if you have an algebraic variety, at each point you can measure the dimension of the space by just looking at let's say that F is a smooth point, then you can just look at the dimension of the tangent space. But otherwise, you have to look at the dimension of the components of this space. Yeah, I can say that more precisely, I guess at the end. But say that we have a dimension like this, so at least one, meaning that we can deform. So we are assuming that we can deform. And then the lemma says that there exists a rational curve on X through F of C. Okay, so that's one of the lemmas. Lemma two, so now we're saying if we can deform, we are done. We can produce a rational curve to our point. Lemma two is if characteristic of the ring is positive, then we can make sure, after changing the map f, after changing f, that or I want to say this is after changing, after precomposing with Frobenius, then we can make sure that the dimension that we were seeing in the previous lemma is greater than or equal to 1. However, we have to precompose with the Frobenius map. So I described the Frobenius map in the case of a ring, which means that it's a map on affine schemes. You can define it as a map on projective schemes, where you just do it locally. And I'm saying that the dimension of the space C, yeah. So we can ensure this in positive characteristics. And the interesting observation about Frobenius is it does not change the space. So as a map of topological spaces, Frobenius keeps the space intact, but changes the ring on the space. Yeah, like the map is not the identity map on the ring. And why is this useful? Well, precomposing by Frobenius as many times as needed, we can ensure that even though we're the same curve, this increases the degree, but does not change the genus of the curve. And why is this useful? Because there's a bound on the dimension of this space, and the bound involves just degree and genus. And if we can control the genus and can control the degree, so we can make sure that the degree is large enough while not changing the genus, we can actually say that the dimension of this space is at least 2 if we twist by Frobenius far enough, recompose by Frobenius far enough. And then there's some more that has to be said, which is, now are we done? Well, we are done in characteristic P, because we have this lemma which says there exists a rational curve in X through F to C if this dimension holds, if this dimension bound holds, and then we're saying that this dimension bound holds in positive characteristic. But then the question is, what about characteristic 0? Because that's really like the initial case of interest. And the idea is that you can lift this information from characteristic P to characteristic 0. And to do that, we actually need to make sure that the curves, the rational curves we're creating, don't have a high enough degree. So if F is a map from P1 to X that we have created, we actually want to ensure and say that the dimension of the Helm space P1 X F0 infinity is at least 2, then what we can do is the format to get a rational curve through, and there's a technical point why we need now 2 points and not just 1, is because P1 has more automorphisms. The format to get the rational point, to get the rational curve through 0 and infinity, that has lower degree. And we can do that if degree of f is greater than or equal to m plus 2. Okay. So what this ensures is that if the degree is greater than or equal to m plus 2, you can reduce it. You can pick a better rational curve. And you can keep doing this to ensure that the degree of the rational curve is at most m plus 1. And the reason why this is useful when doing bend and break is that on the lifting argument, I'm going to briefly say, you need to have some finite dimensional scheme. So a finite dimensional algebraic variety. And the condition that the degree is at most m plus 1 for the rational curves you're looking at tells you that you can actually have such a finite dimensional algebraic variety. So the theorem, I should state this. So X of finite variety of dimension n through for all points x in X, there exists a rational curve C, let's call it Cx, which contains the point x and has degree at most n plus 1. And for degree, you need to have some kind of embedding into Pn. And then to get an embedding, you really need an ample line bundle. And that is going to be given by by the line bundle wedge, the top exterior power of tangent bundle. And one last, I guess we're already 8, so I'll just say briefly, how does the lifting argument go? You try to, well, I'm gonna say this. Yeah, so the point is you can, given a projective variety, you can look at the equations that define it inside projective space. And those equations use finitely many coefficients and finitely many variables. You can adjoin all of those, just join the coefficients to the ring Z. Just adjoin coefficients of defining polynomials for X. And this is going to be a finitely generated algebra over Z. It turns out that for all maximal ideals, so for all M maximal ideal in this ring, let me call this ring R mod M is a finite field. And why this is nice is because we know our result over finite fields. And this is spec R. We know the result over all finite fields. And the finite fields are dense in this ring. So we want to say that the set where the result is true contains an open set. Okay. And to do that, it basically reduces to the fact that you have a finite degree because you look at the space of maps of degree at most m plus 1 from P1R into, let's just say XR, yeah, XR. And this is a finite dimensional space, and it hits all of those points, all the maximal ideals. And by Chevalier's theorem, the image has to be constructible. And that tells you that you contain an open set. And that tells you that you hit the generic point, meaning the generic point is the spec of the fraction field of R. And if you pull back, so what this means is that the result also holds over QF of R, over the fraction field of R. But then you can further pull this back to spec of the ring you were initially working with, and then you're done. The result will hold there as well. It means that there is a rational curve, so map from P1 to X, that goes through a point that we're interested in, has bounded degree, yeah, for arbitrary points X in X. Yeah. And then that completes at least a sketch of the main things one needs to show that final varieties are unirule. Yeah. Are there
Thank
any
you.
questions?
Thank you very much, Shend. So I would like to ask if anyone would like to pose any questions to Shend. Hamdi, do you have a question? Or
Maybe I
yes,
have one quickly.
yes,
Maybe
please, please.
in this last slide, you said that R mod M is a finite field. Is that not normally the case, or is this what is special about the whole story of
Right,
lifting?
so R mod M is just a field in general, and I guess in this scenario, when you're joining a bunch of things to see, what's unclear is we don't know if it's going to be what if this was Q, for example, right?
Mhm.
How do we know that this cannot be Q? Like I can write a variety, like if I have something like this, Q adjoint X, then if I kill X, then this is just Q, right? So this is R mod M, it's Q. And this is definitely not a finite field. But what's special here is having this Z allows you to say that you actually cannot get Q or any finite extension of Q. This is what this result is saying. But in general, you can have like arbitrary fields. Yeah.
Thank you.
Great, thank you. Does anyone else have any questions, Islam or?
Yeah, I just wanted to ask about the general name, about the verbs bend and break. I didn't quite get what's the reference to in the method.
All right. So it's referring to this description here where I said, so the idea of the bend and break was to produce rational curves, or the goal was to produce rational curves. The idea is pick an arbitrary curve, start deforming it, so bend it, and hope that it will break. So that's where bend and break is coming from, because you're bending the curve and hoping it will break, so that you can reduce the genus of the curve and get to a rational curve.
Okay, and this hoping to break, is it something that happens or just in the cases you want to?
Right. So this is bend and break is actually, like, you can see that it is so general that you can apply it in many scenarios. But if we're talking about final varieties, then it is true, and that's what this term is saying. It's saying that if X is final, then there exist rational curves. And the way that we got to them was by proving that we can, in characteristic P, we can deform any curve so that has this bound. Any curve that has this bound, you can deform. And in characteristic P, you can ensure that this bound is true after precomposing with a Fabinian several times. And so you know the resulting positive characteristic, and then you lift it to characteristic 0 using Chevalier basis and the argument with the ring, the joining coefficient Z.
Thanks for the answer and the great talk, Shend.
Thank you, Islam. Are there any other questions? I think in this case, yes, I would like to thank again Shend for this wonderful talk, and looking forward to seeing you here in Prishtina. I hope soon. So thank you very much, and we'll have soon another seminar, but as always, you will receive the announcement via email. So thank you, Shend. All the best to
Thanks a
you,
lot
and
for
thank you
having me.
everyone else. Faleminderit. Zhjeqi. Dhe mirupafshim. Ditën e mirë.
Faleminderit që ndrymësh.
Faleminderit. Ciao, ciao.